All right, let's get started. This is our first lecture for regression and correlation. Correlation is a piece of regression, so it's mostly regression and nothing else. So laugh at this funny joke, and at the end of this series of lectures, at least you'll understand why it's funny. I think it's pretty funny, but then again, I was abused with repeated lectures on regression in grad school. So let's talk about this. This is, I'm not sure I'm really going to stick to where this is in open intro. This kind of wanders in a slightly different pattern. Regression and correlation tries to answer, well, people have broken it down a variety of ways. We might think of it this way. It tries to answer four questions. When we have two variables, two numerical variables that are measured on the same groups of individuals, so paired data, what is the best model for describing the relationship in our sample? So this is descriptive. So like there's a mean that describes something about your sample. Well, there's a number called a correlation coefficient that describes a relationship between two variables in your sample. It's a descriptive statistic. It doesn't say anything about the population. Then we can look at that model after we find the best model, and we say, how well does that model fit the data we have in our hand? How does it fit this sample? And then once we have that model and we've described how well it fits the data, we can wonder how we can use this. We can do some prediction. We can do some other things with the model. And then finally, we do our inferential statistical tests as always. We say, how much do we trust that this model is reflecting something that's really going on in the population, rather than just being kind of a fluke of sampling, a fluke of random sampling effects as we sampled from the population. So the same question we always have about hypothesis testing, whether it's for a t-test or ANOVA or chi-square, how much do we trust that this is coming from a population that looks like this versus this is just a fluke and the population doesn't look like this. So we always start when we're doing regression and correlation with two numerical variables. Two numerical variables is sometimes called simple regression, and you need at least two numerical variables or else there's no relationship to be had. We analyze this starting in the same way that we analyze a single variable, and then we apply that procedure to two variables at once. This has to be paired data, so there have to be a group of participants, cases, subjects. They don't have to be people, as I've mentioned a million times, but they have to be something that has characteristics. And so each participant has, or subject has, two measurements, some value that we call x and some value that we call y. Now, we theoretically call them x and y. In reality, they have actual names like income and social mobility or something like that. X and y in this case can be on totally different scales as long as they're both numerical. With paired t-tests, you needed the x and y to be essentially the same variable or really, really close. But in correlation and regression, they just have to be numerical. You can find a correlation between the price of eggs in Netherlands and number of minutes that people work out on their treadmills. There's almost no limit. So when we talk about these relationships, I sometimes think of them as visual relationships. Sometimes, like some people like the mathematical way of looking things. I think of them visually. So we start with one variable at a time. We know how to do a number line and put observations on a number line. This is a one-dimensional situation. We often call that variable x. So if there's a number line, let's say these are test scores in a difficult course, x is test scores. Let's say it's from 20 participants. And each little blue box represents one person's score. I spread them all out for demonstration purposes so nobody has the same score. There's no stacking in this particular case. So here we go. We can look at the mean of x, which occasionally becomes interesting or important when we're talking about regression. And what if we have y? What if these same participants who gave us these scores also gave us, let's say, their GPA? So 20 participants gave us both a test score on some exam in college or something, and then also a GPA. And there's a mean of y as well. So we have these two variables. Well, the way we analyze this is we turn this into two dimensions by turning one of these variables at 90 degrees from the other. So we leave x the way it is, but we make y vertical instead of horizontal. And now we can cross things in space. Every participant has both a y and an x score. So if a y score is up here above 3.5 and an x score is over here, then we have this dot. And this dot represents one participant, one person in our study. Now, like I said, they don't have to be persons, but they have to be something. And so we can keep watching these dots appear And each dot represents two things. Each dot, because it's in a two-dimensional space, represents both a y value and an x value. Now, in a mathematical sense, it doesn't matter whether you put GPA as the x or the y, etc. But rationally, it often makes a difference. It often matters which one which variable becomes x and which one becomes y. But we'll talk a little bit more about that later. In this case, we see a positive association. Now, positive association is characterized by the scatter plot that seems to kind of move up and to the right. Now, if it was doing the opposite, like crossing this, that would be a negative association. Positive association means that in general, people who have higher GPAs also have higher test scores, or people who have higher test scores also have higher GPAs. It could be argued that I should have put test scores on the vertical axis. I don't know. Depends on what kind of test scores they are, I suppose. So here's another example. Some car data. Some cars, their prices in, I don't know, 2010 or something like that. And their efficiency, how many miles per gallon they get, how many miles they can travel on a gallon of gas estimated. So we can plot those two things. We've got miles per gallon over here, and we've got price over here. And you see there's kind of a negative relationship, although it looks like it might be maybe curvilinear negative relationship. So this is a scatter plot. Each dot is one car here. One dot equals one car. So this is one way we start describing the relationship is visually, but we also use numbers. And one of the most common ways that we use a number to describe a relationship between two variables is a correlation coefficient. Sometimes people will say it's just a correlation, or correlation is the process of calculating correlation coefficients. And that's Carl Pearson, the guy who invented the correlation coefficient. And he is a sexy beast. Here he is. Check out those clothes. That's impeccable taste right there. 1890. So Pearsons R, sometimes called Pearson's product moment correlation coefficient, is a measure of the association between two variables. You always pick some kind of a letter when you come up with a new statistic. And Pearson came in early in the game, so he got R. He could just pick it. And this tells us two things about the relationship between two variables. It tells us how strong that relationship is, and it tells us what direction that relationship goes in, whether it's positive or negative. Those two things both are available with Pearson's R. It's a simple number, but it's either positive or negative, and it has a certain value to it. So this is part of the regression analysis process, and the regression analysis process is bigger than this. It's kind of a big field with lots of toys in it, and this is one of the toys. So calculating Pearson's R is not actually mathematically terribly complicated, although learning at it at first there's a lot of little details, but I'm not going to make you calculate it, but I would like you to understand how it is calculated. So let's look at this data. Let's look at our test scores and our GPA. This seems to have been the thinking that Pearson was using when he thought about when he developed the correlation coefficient as a measure of an association between two variables. He was thinking to himself, what if I standardize these? So standardization, in other words, turning into z-scores, makes our variables have two very interesting properties. One is that 0 is the middle point, and 2 is that anything above 0 is positive and below 0 is negative. And this is useful, Pearson was suggesting, for the following reasons. Now that we've turned our test and GPA scores into z-scores of themselves, and then now we can divide up mentally the space in a scatter plot according to these quadrants, whether you're above or below the 0 points in the z-scores, which means if you're above or below the mean on each variable. So the 0 point is the mean. So here, let's look at what that means in terms of what Pearson came up with. He said, what if I just add up for every score its z-score on y times its z-score on x. So a score is z-score on y times, or an individual z-score on y times its z-score on x. That's a cross product. A cross product is multiplying across something, like multiplying across x and y. So this first person here, that's their dot. They have a very high z-score on y, relatively speaking, and a very high z-score on x. 1.52 on x and 1.66 on y. So if you multiply 1.52 times 1.66, notice they're both positive because 1.52 is above the mean of y. It's over here. Or sorry, above the mean of x. It's over here. and the z-score on y is positive, meaning it's above the mean of y. So you've got two positive numbers. When you multiply them by each other, you get another positive number, 2.52 in this case, zx, zy. Let's take a different dot there after noticing this. Let's take a negative dot. And this negative, it's not really a negative number necessarily, but it's negative when we turn things into z-scores, and all that means is that it's below the mean on some variable. And it's below the mean on both variables. It's below the mean on x, it's below the mean on y. When you multiply the z-score for this, these two z-scores together, what are you going to get? A negative number or a positive number? You're going to get a positive number because a negative times a negative is a positive. So negative 1.37 times negative 1.26, zx, zy is 1.73. So, in both of these quadrants of the graph, the lines don't have to be there to just help us think about this. Everything above the mean of y and above the mean of x will be positive if we multiply its z-score of x times its z-score of y, the z-score cross product. And everything below the mean of x and y will also be positive. So you see how it sort of makes a line there. So if we add all of these things up, it'll be kind of a biggish positive number. Or if we take the average of them, it will be a noticeably positive number. But sometimes you have a negative score times a positive score. So this individual right here, they have a below average test score but an above average GPA. Therefore, if you multiply the z of their test score times the z of their GPA, you get a negative number. Negative 0.47 times negative 0.7, or plus 0.72, you get a negative number. And that's the case for everything in these two quadrants here. So here we have this situation. Everything that's in these quadrants, the upper left and the lower right, will be negative if we take a z-score x times z-score y. The result would be negative. And everything here, the upper right and lower left, that would be positive. So in this case, if we were to add up all of the cross products, all of these zx, zys, the result would be positive. And if we took the average of those cross products, the result would be positive. And that's a correlation, the average of these. And so you can see if the stuff is falling along a diagonal line like this, you're going to get a positive number. If it's falling along a diagonal line like this, you're going to get a negative number for the correlation coefficient. And if it's all over the place, the pluses and minuses will cancel each other out, and you'll get a zero correlation. So here's another example. The amount of alcohol you drank last night versus your test score. We can convert these into z-scores. You see it goes into a 0 as the middle type situation. And when we do that, we can imaginarily draw lines here, and then we've got a similar type situation. Everything in the upper right will be positive if its zx times its zy is calculated. Everything in the lower left will be negative. Upper left will be positive. Upper left will be negative, and lower right will be negative. So there's a lot of negatives here, and not much in the way of positives. So if you add all these up or take their average, you're going to have something negative. And indeed, this is what a negative correlation looks like in a scatter plot. The line more or less drops from upper left to lower right. So we usually write correlation coefficients just as R. If we're thinking about it, we italicize it. Now, R has to have a sign. If it doesn't have a sign, it's assumed to be positive, as most normal numbers are. And it always goes between, it can't be bigger than 1 or smaller than -1. And so we don't usually put a 0 in front of it, 0.42. Computer software sometimes does, but when we write it out ourselves, we just put negative point or plus point. So the negative sign, if it's negative or if it's not there, it means it's positive, shows us the direction of the correlation. This is a negative, so this means it's a negative correlation, so the number is going from upper left to lower right. If it were positive, it would mean it was a positive correlation. And then the absolute value of the correlation coefficient tells us how strong it is. So negative 0.42 is just as strong as positive 0.42. It's just reversed in direction. And it's very easy to reverse the direction of a correlation by just redefining your variable to be like opposite day variable. So this variable is happiness. Oh wait, now this variable is sadness. Now you have a negative correlation instead of positive. So don't pay too much attention to negative or positive, although you have to pay attention within a particular problem, but it's very easy to reverse that. So a positive correlation is when two things vary with each other directly, when high values on x are associated on average with high values in y, or low values on x with low values in y. So there's a relatively strong positive correlation. There's a weaker positive correlation. Now these lines are sort of like the best fitting lines, the line that is the least distance on average from all the dots put together and still is a straight line. That's a regression line, or a line of best fit. We'll talk about that later. A negative correlation is when low values on x are associated with positive values on y, or the other way around. Now an example of a negative correlation might be, number of alcoholic drinks you had last night versus your score on the test. Larger number in alcohol will be lower number in tests on average. Or number of policemen on the streets versus number of crimes per capita, so more policemen is fewer crimes. That's a negative correlation. It doesn't mean it's unhappy or bad, it just means it's an inverse correlation. So there's a moderately strong, maybe going kind of weak, negative correlation. And there's a much stronger one, negative correlation. Alright, I'll try and guess what the correlation coefficients on this slide are. What do you think that correlation coefficient is? You should definitely think it's positive because it's going up and to the right, and it's fairly strong. That's 0.9. That's a nice strong correlation coefficient. 0.1 is as strong as it can be. Yeah, put in the little best fit line there. What about this one? You should notice that it's even stronger than the other one because the dots are clustered more closely to each other and clustered more like a line. So this one is negative 0.99. That's an extremely strong correlation. So this one, that correlation is 0.5. This one here, it's going to be negative because of its orientation, right? The line, the best fit line is going to kind of go down and to the right. Negative 0.7. This one up here. That one's a negative 0.3. And here, it's actually a correlation of 0. 0 looks like a shotgun blast. There's no way to draw one line that's a better fit than any other line through a 0 correlation. Now, perfect 0 correlation is very rare, but things that are really low, like 0.1-ish, that's much more common. That's kind of 0, really, in reality. Now, you can try this yourself if you want. In R, you can take any two variables, so do any data set you want, and plot x and y. So plot x comma y. And then you can add a mean line for x. This way, you can say AB line, and then parentheses v, so like vertical is at mean of x. Now mean of x, oops, I forgot to put a parenthesis in there. Let me fix that, hang on. Alright, I fixed it and improved it. You can have a vertical line at the mean of x. You have to put N8 at RM equals true. I put just a capital T, but you could type out true in all caps if you want. That means remove all the missing values. You have to do that with real data that has missing values. And you can add a horizontal line for y. AB line, H horizontal, equals mean of y. So, feel free to do that. It's kind of neat. That just kind of divides up your scatter plot, and you can look at the quadrants. How many dots are in upper left, lower right, etc. So the formula in the book for calculating the correlation coefficient is just a teeny bit confusing. You don't need to memorize it. It's got a lot of stuff in it, but after you do this a while, you realize it all makes a lot of sense. I hope you notice that things like the deviations of x from its mean, the deviations of y from their mean, and then divided by their standard deviations. This is kind of a z-score type thing here. And then 1 over n minus 1. Like this whole thing could be over n or over n minus 1. So, and then this is the sum up of all these. So you can see that there's some averaging, some standardized z-scoring type thing going on there. So an easier to understand formula, a conceptual formula, I don't think it's practical for calculating in real life, is this. And in fact, it should probably be n minus 1 instead of n, but I'm not 100% sure of that. Anyway, we're not going to calculate much in the way of correlation coefficients in this class by hand anyway, but I would like you to understand what they are. This is it. This is the sum of the cross products divided by n. So it's the average of those zx, zys. So those green pluses and orange minuses on the graphs, that's all this is. That if you add all those up, all their sizes, you get r, as long as you divide by the number there are. So if you look at the average of the plus minusiness of those graphs, that's what this is. Zx, zy for each point, summed up. So the upper right and lower left will be really big and positive. The lower left and, the upper left and lower right will be really big and negative, so maybe they'll cancel each other out, etc. It's the average of that. So here's another scattergram, and this is the cars again. And so we could practice calculating the correlation coefficient here if you want to. So go ahead, if you feel like getting the practice, and calculate yourself a correlation coefficient. I'll wait for a few seconds so you can pause before I show the answers. Okay, here's the z-score of price. This is a really inconvenient way to calculate the z-score, or calculate a correlation coefficient, because you have to turn everything to the z-scores first. And here's the z-score of miles per gallon. Multiplying the z's together, you get that. The sum is that. You divide by 8, negative 0.84. So that's that correlation coefficient. It says it's a value of negative 0.84. And we're all done with that. That's that lecture right now. Next we'll get into some more correlation, and it'll be so much fun you might pass out. So bring a pillow. You should be sitting down before you watch the next lecture.